Over the past few lectures, we've been examining methods of indexing X-ray powder diffraction patterns. And we saw that for cubic crystals, this process is relatively straightforward. However, as the symmetry gets lower, it becomes increasingly difficult. And for mini crystals, the only practical way to do this is to use a computer. That approach is called autoindexing. And in this lecture, we're going to look at approaches to autoindexing powder diffraction patterns. I do want to say that this is really an important skill. When you have a powder diffraction pattern, if you cannot index it, you're completely stuck, and you really can't get very much information from your diffraction pattern. Now, when we think about the indexing problem, it's useful once again to think about the differences between single crystal diffraction and powder diffraction. In a single crystal experiment, as shown on the left, we have an incoming X-ray beam, it strikes our crystal, and in certain specific directions we get constructive interference, and that gives rise to diffraction peaks that we can detect at the detector. The pattern depends on the orientation of the X-ray beam and the crystal, but we have these specific spots. Now imagine you were going to rotate the crystal around the direction of the incoming beam. If you did that, all of the spots would move. But in order to keep the 2 theta angle the same, in order to satisfy Bragg's law, they would move in a circular path around the direct beam. When you do a powder diffraction experiment, it's kind of like we do that. It's kind of like we move the crystals around the direct beam. We're not actually moving crystals. It's just that we have thousands upon thousands, tens of thousands of small crystals in our sample. And for every possible orientation, there's a crystal that's oriented in that way. So it has the effect of, first of all, bringing all of the diffraction peaks into the detector. And secondly, instead of seeing discrete spots, we see rings or circles, which are where the cones of diffraction intersect our detector. Now, when you get a single crystal diffraction pattern like this, if you were to orient the crystal so that it was lined up in a specific high symmetry direction with the incoming beam, for example, here we have the X-ray beam coming in parallel to the 001 axis of the crystal. And when we look at this diffraction pattern, we can see that the pattern is a square pattern. And so that tells us that the cut through the reciprocal space lattice that's perpendicular to this beam has square symmetry. And that tells us that the crystal is either a cubic crystal or a tetragonal crystal. So that's a huge help in trying to figure out what is the size and shape of our unit cell. Not only that, but once we see that, we can index the individual peaks. This is the 100 peak. This is the 010 peak. The 1 bar 00, the 01 bar 0. Once we see that, and calculating the distance from here to here and doing a little trigonometry, we can figure out the length of the A axis or the length of the B axis. You could draw a circle which has its origin on the direct beam, and all 4 of these diffraction peaks would fall on this circle. In a powder diffraction pattern, because we're rotating the crystal about the incoming beam direction, if we were rotate it by 10 degrees, all of these peaks would rotate by 10 degrees. And if we were rotate it by 1 degree increments and collect a diffraction pattern at every step, we would get this ring, which is what we see in a powder diffraction experiment. The next ring would be the one shown in red here, which intersects the 110 set of diffraction peaks. Then you have a ring at yet a higher distance out from the origin, which intersects the 200, the 020, the 2 bar 00, and the 02 bar 0 peaks. Then we have this green ring, which intersects the 210 peaks. In a powder diffraction pattern, we're not going to see those spots. We would, if we had a flat detector, an area detector, see rings. Now, when we look at a more typical diffraction pattern that we get from a diffractometer, what we basically are doing is taking a cut along one direction a radial direction out from the center through each of these rings. And everywhere that that cut intersects one of the diffraction cones, we see a peak. And that's what we see in this powder diffraction pattern. But when you look at this powder diffraction pattern, I think it should be kind of obvious. It's not so easy to look at this and say, oh, that corresponds to a square reciprocal space lattice in a certain direction. So we cannot very easily look at a powder diffraction pattern and tell if a crystal is hexagonal or tetragonal or monoclinic. So how do we go about assigning the indices to the peaks? All of the mathematics in this process are contained in this top equation. So we've got on the left-hand side 1 over d squared. Right? When we were indexing manually, that was the parameter we were trying to fit. And then we have here 6 different terms. And in each term, the part in parentheses tells us about the size and shape of our unit cell. Here specifically in reciprocal space. Now, for every peak in the diffraction pattern, we'll have a different HKL. But the things that are in parentheses, which are giving information about the size and shape of the unit cell, those are the same for every single peak. So mathematically, the equation reduces to this. Our task is to find the integers h, k, and l, which are different for every single peak, then when multiplied by these constants, allow us to index or explain the d-spacing of every single peak. Oftentimes we might use the term q. The variable q is simply equal to 1 over d squared. Now, this long expression that has 6 variables, it reduces to simpler expressions if some of the angles are 90 or other specific values, or if some of the lattice vectors are of equal length. Right? But in general, we don't know what is the crystal system when we go to do the indexing. So we're going to use a computer program to solve this problem. There are a variety of programs you can use for auto-indexing. Here I list some of the more common ones. The most modern of these is implemented in the Topas software suite. That's the one we're going to talk about exclusively. That's the one we're going to use outside of class. Trior is one of the oldest ones. It goes back initially to 1965. And the approach that Trior takes is to more or less make guesses at what are the indices of different low-angle peaks, and then use those, build up from there to try and index the peaks. Topas uses something actually very similar, but it's sort of a more modern implementation of this approach used in Trior. Dickval is somewhat different. In Dickval, you're going to systematically search all n-dimensional space. So you're going to start by saying, okay, I think the crystal is cubic. Now I'm going to search up to a certain volume, all of the possible cubic unit cells. And then if that doesn't work, let's try tetragonal, and then hexagonal, and then orthorhombic. So Dickval is a more computationally intensive approach. It tends to take more computer time. In these days, that's not really a big downside, but it's not great for low symmetry structures, and it's also can be rather easily thrown off by impurity lines. So back in the days when I used these programs, when I was a grad student or a postdoc, I generally had more luck with Trior, but Trior also has some issues if you get down to very low symmetry structures. Crisfire is actually a suite of, I think, up to 7 different auto-indexing programs, including Trior and Dickval, at this site, at least at the time of this lecture. The typical auto-indexing program gives you several solutions, maybe dozens of solutions. And so when you look at this, you first have to say, well, which solution is best? By the way, that's not always obvious. You also have to say, are any of these solutions really valid? I mean, it's almost always going to give you something, but sometimes the solutions it gives you are not meaningful. So we need some way to quantify the quality of each solution. And that's given by this de Wolf figure of merit. And the idea here is the figure of merit, which is called M20, is based on the input of the first 20 diffraction lines in your pattern. The numerator, Q20, is just the Q value, that is the 1 over d squared of the 20th diffraction peak. So you can easily calculate that from its 2 theta value. The Q that's given down here in these brackets is actually the average discrepancy in Q averaged over all 20 peaks. So this is how far is the Q observed and the Q that's calculated from our unit cell, which of course is related to how close is the 2 theta value that we're calculating with this unit cell from the 2 theta value that we observed. So the closer the peaks are to where they're supposed to be, then this is going to be small, and that's going to make our figure of merit large. And then this last term here, N20, is actually really important. This is the number of peaks that would be calculated up to the 2 theta value where the 20th peak is observed. And the reason why you need that is if you make the unit cell large, well, you're going to get more and more peaks. If you make the unit cell symmetry low, go from cubic down to triclinic, you're also going to get a lot of peaks. So large, low symmetry unit cells give us a lot of diffraction peaks, and just accidentally, many of those diffraction peaks might match up where the experimental ones are. But they're also going to give us a lot of peaks where there are no peaks. And so this term penalizes you if there's a lot of missing diffraction peaks. One thing to note is that if you can run the indexing and you can index the first 20 peaks and your figure of merit is bigger than 10, that is almost certainly going to be a valid unit cell. Sometimes it's not exactly the right unit cell, but is geometrically related, so it's very close to the right answer. So if you get M20 bigger than 10, this is something you should pay attention to. If it's less than 10, it's probably questionable. Another figure of merit that's sometimes used, which is closely related, is called the F-index figure of merit. It's almost the same, but just with a few details in the numbers we're putting in. Here, we're putting in the number of observed peaks. So you can use any number here. We might put in the first 15 peaks. This, instead of being the average discrepancy in Q, is actually the average discrepancy in the 2 theta value. How far is the calculated 2 theta value from where we see a peak? And of course, the smaller that is, the more accurate the peak positions, the bigger your figure of merit. And then this term, N theta G, is very similar to what we saw in the de Wolf figure of merit. This is just the number of peaks that could be present up to the nth peak that you put in. More or less, this is a very similar figure of merit. Topas uses basically the de Wolf figure of merit, but with another term that takes into account the fact that there may be some unindexed peaks in our diffraction pattern. So let's say you put in the positions of 20 peaks and you get an answer, and that answer explains the positions of 18 peaks, but there's 2 peaks that are not accounted for. There is no way to quantify that in the earlier figures of merit, but here what it's going to do is going to say, okay, there's 2 impurity peaks. So this second term is going to be 1 over 2 plus 1, so 1/3. So that would cut our figure of merit down by a factor of 3. If there are no unindexed lines, no impurity peaks, of course, this last term just reduces to 1, and we get something that's identical to the de Wolf figure of merit. What are some parameters which determine whether the indexing might be successful or not? So here are some things that matter. Your chances of success depend on how many diffraction lines you put in. Any inaccuracies in the peak positions, either random or systematic, can have a deleterious effect on your chances of success. If you have impurities or secondary phases, that is, there are some crystals in your sample which are a different phase, the more of that you have, the harder it is to index a diffraction pattern. And then there's something called the dominant zone when one or more of the unit cell axes gets very small. I'll talk a little bit about that at the end. So let's start by thinking about the number of diffraction lines. So here are some statistics from Coelho's paper where he describes his indexing approach. And what he did in this paper is he generated a bunch of hypothetical unit cells and said, okay, here's a bunch of peaks. Can my program index it? When the symmetry is high, cubic, tetragonal, hexagonal, the kind of things that we can sometimes do by hand. I mean, the program basically works almost all the time. But as the symmetry gets lower, sometimes it's not able to come up with the right answer. This shows that that number depends quite a bit on how many peaks you put in. If you include only the first 10 diffraction peaks, then about 3/4 of the time it can still find the right answer for an orthorhombic crystal, but that goes down to only 30% of the time if we have a triclinic crystal. And maybe that shouldn't be too surprising. Trying to fit the positions of 10 peaks with 6 variables is not a very highly overdetermined problem. If, on the other hand, we double the number up to 20 diffraction peaks, right, that's what de Wolf suggested, then you can see that the orthorhombic success rate goes up to 98.5%, and even the triclinic goes up to 88%. So as a general rule, we want to put in more peaks, not less, as long as we can accurately determine their peak positions. But it is true that the low-angle peaks are more important than the high-angle peaks. And because of that, usually 20 to maybe 30 at the top end is about all you really need. And there's not much to be gained by putting in more peaks beyond that. Now, another question is, well, what about if there are errors in the peak positions? You know, the numbers I just showed you, the peak positions are basically all perfect. Here he took a unit cell, and the volume of this unit cell is 2,000 cubic angstroms, so that's a pretty big cell, and he's inputting 15 diffraction peaks. Over here on the left, he introduces random errors in the 2 theta positions of plus or minus 0.003 degrees. And then he puts those new, now somewhat erroneous peak positions into the auto-indexing routine and says, okay, what's the answer? And you can see here that at 2,000 cubic angstroms, the right answer, you have a figure of merit that's over 250. And you have some cells that are very, very close to that, you know, nearly 2,000 angstroms, basically the same unit cell. They all have high figures of merit. But if you move away from that, the figure of merit is 10 or 20 at the most. So in this case, you could easily pick out what is the correct unit cell. If you do that same thing and you have errors of 0.03 degrees in your 2 theta values, randomly assessed, well, look what happens now. Now, your discrimination of the correct answer has really gone downhill. I mean, in fact, probably the highest figure of merit is out here at just above 2,200 cubic angstroms, right? That's not the correct answer. We do see that the correct answer, which is probably right here, still has a reasonably high figure of merit, but it's only 30 and not 300. And you can also see that there's just many solutions, some of them with quite different volumes, that have very comparable figures of merit. So, you know, random errors of 0.03 degrees in your 2 theta value is really bad for indexing. Now, how do we get accurate 2 theta values? You know, unless you have a pattern with very little peak overlap, like a cubic pattern, and you're using monochromatic radiation, you can't just go and say, oh, what's the maximum of each peak? You actually have much better luck if you fit the peak. And in particular, with a lot of lab X-ray data, we have both copper K-alpha 1 and copper K-alpha 2 radiation. Those have slightly different wavelengths. You can see there's a black line where each of those 2 peaks should be found, and you can see that they're very close together. You get into an intermediate range, and there some splitting kind of occurs, but not really enough to resolve. And so this is kind of throwing off where the peak maximum actually is. What we want to do in the auto-indexing is the position of this first black line. And when you get out to yet higher angles, now you can see you can actually clearly resolve the K-alpha 1 and the K-alpha 2 peaks. Here it actually would be somewhat easier just to pick the top of this first peak. The other thing that happens is, you know, this is a cubic pattern, but what if we had accidental peak overlap? Then it gets kind of really hard to say exactly where the peaks are just by looking at it and picking a maximum. And in those cases, we really need to fit the peaks. And most software programs, Topas, for example, will allow you to do that to obtain the peak positions. There's another kind of error, which is a systematic error. What I just talked about were random errors, but sometimes all of the peaks are shifted by a specific amount. Now, that might happen due to what's called a 0-point error. Maybe your diffractometer is not calibrated correctly and all of the peaks are shifted by 1/10 of a degree too high or too low. A more common thing, which is harder to get rid of, is what's called a sample height displacement. So when you prepare your powder sample, oftentimes it might be in a flat plate, and you're going to smooth out the top of that powder, and it should be right at the top of the sample holder. And if it's off a little bit, that actually leads to a shift in the peaks. And this is the formula that gives the shift of those peaks. The displacement height times cosine of the theta value at wherever the peak is, divided by r, and r is the goniometer radius. So this is the distance from the crystal or from the powder to the detector. This is for a goniometer radius of 320 millimeters, 32 centimeters. That if we were to have the sample displaced by 0.05 millimeters, that doesn't seem very big, that we get an offset in our theta of just below 0.01 degrees. If the displacement goes up to, let's say, 0.1 millimeter, now we're up almost to 0.02 error. And remember, this is theta, so the error in 2 theta would be double this. And once you get up to, let's say, 1/4 of a millimeter, which is probably something you could visually see, you can see that you're introducing really quite a large error. The other thing I'd like to say here is that if we're only collecting out to maybe 70 degrees, which might be typical for indexing, you can see that this function doesn't vary by much. And so generally, we're just going to use the 0-point error. It's not generally possible to deconvolute a 0-point error and a sample height displacement. And for indexing, typically it's just simpler mathematically and a good approximation to use just a constant 0-point error. Now, in the Topas paper, Coelho says that as long as your 0-point errors are less than plus or minus 0.052 theta, it really shouldn't hinder your indexing efforts very much. I will tell you from experience that the older programs like Dickval, Ito, Trior, a 0-point error of 0.05 degrees 2 theta will make a really big difference, and it'll make it hard for those programs to get the right answer. Now, how do we avoid these systematic errors? Well, first of all, we want to make sure our diffractometer is calibrated, and then when you prepare your sample, you want to do all that you can to make sure that the height of the powder is exactly flush with the top of the sample holder. Some other things you can do beyond that, one old school technique is to add something as an internal standard. So if you add a little bit of silicon or sodium chloride or something where you know the lattice parameter very precisely, you know exactly where those peaks should be, and depending on where you see those peaks, you can then set up basically a correction curve to account for any errors in the peak positions. Something that's maybe a little less involved but maybe still useful is checking higher order diffraction lines. So let me give you an example of what I mean. Let's say we had a cubic crystal with a lattice constant that's exactly 4 angstroms. So the 100 peak would have a d-spacing of 4, and the 200 peak would have a d-spacing of 2. And they would come at these 2 theta angles. Now, if we were to introduce a 2 theta error of 0.1 degrees 2 theta, right, this would go from 22.2 to 22.3. This would go from 45.29 to 45.39. Now, if you look at these two values, which are calculated from these 2 theta values, you'd see they're no longer exactly in a 1-to-2 ratio. If you double 1.996, you're going to get 3.992, not 3.982. So you could then shift all of the values by a constant 2 theta value until these go back into exactly a 2-to-1 ratio. So that's a way you could internally estimate your 0 point. And in fact, this is the kind of thing that Topas does. Probably the most challenging thing to auto-indexing is that you don't always know a priori if your sample is a single phase. you don't know if all of the diffraction peaks go with one and only one phase. And if you have a mixture of two different crystalline phases in there, and there's peaks of both in significant numbers, it's almost impossible to index it with a computer because it can't find any solution that would explain two phases that have no mathematical relationship to one another. In the paper here shown at the bottom, what Coelho did was to take these data sets that were perfect and just introduce then some spurious impurity peaks and see what that did to the success ratio. So you can see that if he put in 3 impurity peaks, he still was able to get pretty reasonable results. Even in the triclinic case, he could still get the right answer about 2/3 of the time. As you add more impurity peaks, you can see that the success percent goes down pretty dramatically. And of course, it should be stressed that these patterns are also ones where the peak positions are perfect, the peaks that belong. So, there's no doubt that having impurity peaks there is going to be problematic. But it's also true that if you have, only a few impurity peaks, so you put in 20 diffraction peaks and let's say only 2, 3, 4 of them are impurities, there's still a reasonable chance that it might find the right answer, especially if the symmetry is high. Well, let's say that the impurity peaks are really preventing you from getting to the right answer. Or you look at a solution and it suggests some of the peaks might be impurity peaks. How do you know that they really are? Here's a couple of things you can do. Oftentimes, different phases have somewhat different peak shapes. So if you have one set of peaks that are broader than the other set of peaks, well then that's a kind of a clue that they might go with a different phase. It's not foolproof because there are other effects that can lead to different broadening of peaks within the same phase, but that's oftentimes a strong clue. You could also remake your sample, and if you remake it, usually you don't get exactly the same ratio of the two phases. So if you remake your sample under, let's say, slightly different conditions, and you end up with some peaks all get a little bit stronger or they all get a little bit weaker, that's probably a good sign that they go with a phase that's different from the main phase. You can also try matching your powder pattern to the powder diffraction file. And sometimes you can use complementary spectroscopic probes to assess the purity of your sample. So I've been involved in projects where somebody might have done, let's say, solid-state NMR, and from the NMR they could tell how pure their sample was. So those are a few things you can try and do to assess the purity of your sample if you feel like that's what's preventing you from indexing your pattern. The last thing I want to mention is something called a dominant zone. This doesn't come up very often, but when it does come up, it's definitely problematic. And the idea is, what if our unit cell is very anisotropic? And specifically, let's say that we have two axes that are quite big and then one unit cell vector that's much smaller than the other two. Well, remember that small unit cells give you peaks at high angles, and large unit cells give you peaks at low angles. That's kind of the inverse relationship. That means in the first several peaks, you might not have any that represent that small lattice parameter. So here's an example. I took this from this book, Structure Solution from Powder Data. And it talks about a pharmaceutical compound where the true unit cell is given here. Notice that the B lattice parameter is much smaller than the A and the C. And so then if you were to just calculate where the peaks should be for this unit cell, you would find of the first 40 peaks, the K parameter is 0 for all but one. Right? So then it's really impossible to figure out what is the B lattice parameter. And so in the indexing, what the program did is it gave a B lattice parameter that was completely wrong, but despite that, it got the A, the C, and the beta correct. And so the F40 figure of merit was over 2,000. But yet that unit cell was still incorrect. Well, let's finish by just doing an example, okay? I've taken an example from my research group. This is a pattern of this quadruply ordered perovskite cesium-4 manganese bismuth 2 chloride. Here's what the powder diffraction looks like. This is a copper radiation lab data. This is collected on an instrument, the Bruker instrument in the crystallography lab that doesn't have any K alpha 2. And from this, my student Noah was able to determined the position of 46 different peaks, and he gave that to Topaz, and those 46 peaks were the input to the auto-indexing program in Topaz. Here's what the output looks like. Okay, so we have a lot of solutions here. These are all of the solutions where the goodness of fit, or the figure of merit, is greater than 10. Remember, for the de Wolf figure of merit, we said greater than 10 means that it's probably a meaningful solution. But then, what does it mean when there's so many that have meaningful figure of merit? Well, we have to look a little bit more closely at the data. And when we do so, we see that actually not all of these solutions are unique from one another. See this top line, if you look at it, which is a hexagonal cell, is more or less very similar to this one and this one and this one, these four solutions, right? They all have basically the same volume, basically the same lattice parameters. Entries 2, 3, and 4 are all a cubic cell that's about 21.3 angstroms. They differ a little bit in the choice of space group, and that will introduce some systematic absences that lead to slight deviations in the figure of merit here. But for now, let's just consider those all basically the same solution. Then down here we have something similar. This is a cubic space group that's only about half as big. And then we have another set of equivalent rhombohedral solutions. So let's simplify this and say, really, although there's a bunch of entries in that table, there's really only 4 different flavors of solution in the table. We have a rhombohedral space group, and it's indexed in a hexagonal cell. That's got the highest figure of merit. We've got 2 cubic solutions, and they differ from each other in that this upper one, which has a higher figure of merit, has a doubled lattice parameter. So that means its volume is 8 times bigger. This is a pretty big unit cell. Its volume is almost 10,000 cubic angstroms. Then we have, this other cubic cell, and then finally we have a rhombohedral cell, very much like the first one, but the C-axis is only half as big. Okay, so 2 rhombohedral solutions, 2 cubic solutions, all with different volumes. How do we differentiate between the two? Well, it is true that the solution at the top has the highest figure of merit, and the top 2 definitely have a higher figure of merit than the other 2. And the reason why their figure of merit is so much higher is because the bottom 2 fail to index 14 of those 46 diffraction peaks. So when you've got a solution that indexes all of them versus a solution that doesn't index 14 of them, that's a really strong indication that we should go with the solution that indexes all of the lines. Now, what about these 2? Their figures of merit are not that far apart. But then we want to do a couple things. We want to look for solutions that are high symmetry and give us a small unit cell volume. Now, the hexagonal cell in line 1 is slightly lower symmetry than the cubic solution in line 2, but it only has one more variable, the hexagonal cell. So that's not that much lower in symmetry, and the unit cell volume is much, much lower. Really, when I look at this data, it's pretty clear that the right answer should be the top line. It's got the best combination of indexing all the lines, relatively high symmetry, and a small unit cell. Now, if we wanted to compare, let's say, these bottom 2 solutions, in particular this F23 cubic cell, which has a volume that's still even smaller than the R3 hexagonal cell, what's going on with these 14 unindexed lines? And here I'm zooming in on the powder pattern, and I've got a red arrow everywhere there's one of the diffraction peaks that's fit by the rhombohedral cell, but not by the cubic cell. And what you can see is that, okay, all of these peaks are really pretty weak. So it would be kind of easy to overlook them and conclude that the cubic cell is the right one. But, we've analyzed this diffraction pattern in detail, and there's no doubt that the rhombohedral cell is the correct one. And a big clue to that is to say, wow, there's 14 small peaks in there, and those are all explained by the rhombohedral cell. I mean, the chances that we just happen to have an impurity that matched those 14 different peak positions is Very slim, right? At the end of the day, it requires a little bit of skill. You might even say it's a little bit of an art how to interpret the outputs of the auto-indexing program. But hopefully what we've discussed in the lecture today will give you some logical principles to apply to that process.